The standard reduction potentials for reduction half reactions are typically given in tables. So given that this one is an oxidation half reaction, we'll just reverse this reaction and flip the sign. And these are standard cell potentials, where we have a 1 molar concentration of the species involved. Now the larger the potential, the more likely the oxidation or reduction half reaction is likely to occur. So for example, zinc is more likely to be oxidized than chlorine. And we can calculate the standard potential of the cell using the standard potential of the oxidation half reaction and the standard potential of the reduction half reaction. And note that for this reduction half reaction, for example, we multiplied it by 2 to match the electrons and sum up those half reactions to get the redox reaction, but we never multiply the potential by a coefficient, because it's an intensive property that doesn't depend on how much of the species we have. We can determine the standard Gibbs free energy change for an electrochemical cell using the number of moles of electrons that result from the half reactions multiplied by Faraday's constant and multiplied by the standard cell potential, which is obtained by summing up the standard potentials of the oxidation half reaction and the reduction half reaction. So for example, for this galvanic cell, E0 is 1.10 volts, which is the same as joules per coulomb, and we have 2 moles of electrons per mole of reaction, and Faraday's constant is 9.6385 by 10 to the 4 coulombs per mole. So when the units cancel, the result here will be in joules. And note that the redox reaction of the galvanic cell is thermodynamically favoured. So we have a positive cell potential, and for thermodynamically favoured reactions, delta G0 is less than 0. So that's why we have this negative sign here. And by the same logic, this electrolytic cell has a redox reaction that is not thermodynamically favoured. So we have a negative standard cell potential, and therefore negative by negative gives a standard Gibbs free energy change greater than 0, as expected. Consider a galvanic cell that's driven by the following redox reaction, where Faraday's constant is given, and assume the reaction occurs under standard conditions. Find the standard cell potential. So that's equal to the standard potential of the oxidation half reaction plus that of the reduction half reaction. So assigning the oxidation numbers, we can write the half reactions as follows. So zinc loses 2 electrons, so that's being oxidized, and silver gains an electron. So given that these are reduction potentials, we reverse the reaction and thereby reverse the sign of the potential. And for the reduction half reaction, we'd multiply it by 2, so the electrons cancel to get the total redox reaction, but we don't multiply the potential by 2 because it's an intensive property. So therefore, if we sum these together, we get a cell potential of 1.56 volts. And the standard Gibbs Free Energy change is calculated as follows, where we just calculated the standard potential of the cell, and volt is joules per coulomb. And if we substitute Faraday's constant, and this reaction results in 2 moles of electrons per mole of reaction. So these units cancel. And to get this in kilojoules, we multiply by 10 to the minus 3, which gives the following result. Using two significant figures.